Hello, everybody. My name is Nicholas Palumba, and today I will be talking about DSP energy management. So, welcome to my TED Talk. So, the news article that inspired me to have this talk is entitled Strategies for Power Efficient Machine Learning at the Edge, dated September 8th, 2021. This article raises the concern for challenges associated with energy and power management in digital signal processing applications on edge devices. So, traditionally architected edge devices waste a significant amount of energy by operating in the standard digital signal processing paradigm, in which all the sensor data is digitized at the start of the signal chain, regardless of the relevance to the task at hand. So the writer focuses on new options he identifies for extending battery life in these always-on edge devices. So why do we care about this? Well, as human beings, as I'm sure you guys know, we are naturally lazy. And this helps us achieve more for less. So energy management is critical to allow DSP to be used in edge and Internet of Things devices. So the proliferation of highly functional edge and IoT devices has the potential to increase efficiency and productivity for us lazy human beings by automating an almost infinite number of conceivable tasks. The issue is, however, that energy is often very scarce in edge applications. So first, let's review the theory behind the energy contained in a discrete signal. So as you guys know, in signal processing, the energy of a discrete signal is defined as the area under the squared magnitude of the considered signal, as you know from using Parseval's theorem throughout this course. However, energy in this context is not strictly speaking the same as the conventional notion of energy. In the equation shown here, which is Parseval's theorem, E represents the conventional notion of energy, and Z represents the magnitude of the load being driven by the signal in appropriate units. So for example, if X of N represents the voltage of an electrical signal propagating across a transmission line, then Z would here represent the characteristic impedance in ohms of the transmission line. So the resulting energy calculated by this equation would then be in joules. So upon inspection of this equation, we can clearly reduce the energy consumed by a discrete signal by ensuring that we minimize the quantity of samples taken, ensuring the magnitude of the signal is as small as possible, and ensuring that the driven load, Z here, is as large as possible. Okay, so now let's consider the potential solutions described in the news article. The first mentioned solution is the obvious one. Use lower power digital signal processors and microcontrollers. Clearly, the success of edge computing relies heavily on the rapid proliferation of digital signal processors and microcontrollers. These digital processors can handle the complex analysis of data, such as deciding whether a wake word has been spoken right on the device. However, as pointed out by the author, these processors are still the traditional clock processors that operate within the typical digital paradigm and require digitization of all the analog sensor data before processing. So energy reduction here can only be the result of small incremental improvements as semiconductor improvements are made. So the second stated solution involves detecting ambient activity in the analog domain and waking the digital system when the analog sensor exceeds a certain energy threshold. However, chips of this kind can't determine the type of event that's occurred or whether it's related to the task of the system being implemented. So by providing a very low power always on mode for the system, this approach reduces energy consumption by keeping the digital system off for some of the time. Unfortunately, like I said, these simple analog circuits can't distinguish the type of event, and they typically detect too many false alarms that trigger the digital system wake up. So energy conservation improvements are again only incremental here. And finally, we have the third offered solution, which involves using analog machine learning to detect specific discrete events from analog sensor data, and then only waking the digital system when a specific event has been detected. So chips of this type minimize both the always-on power of the system and the amount of time the system remains on. So these analog machine learning chips operate completely as analog circuits with no clock required, and use raw analog data for inferencing and classification. So basically the importance of data is determined before spending any energy on data conversion and waking the associated digital processor. So clearly these three options offered by the author can be combined to offer practical solutions. However, I now want to turn our focus to the algorithms used in digital signal processing and techniques used to improve energy efficiency in these DSP systems. So, as you all know, the discrete Fourier transform, or DFT, converts a finite sequence of equally spaced samples of a signal, x of n, into a same length sequence of equally spaced samples of the discrete time Fourier transform, or DTFT, x of k. Since it deals with a finite amount of data, it can be implemented in computers or other dedicated hardware. So as such, it's probably the most important discrete transform in DSP, and I'm going to focus on it here. So here we have a reminder of the DFT definition. And on this slide, we have a reminder of the inverse DFT definition. So the complete process is shown here. These operations are useful in many fields, but as you guys know, the DFT and IDFT, computing them directly from the definitions is often too slow to be practical. And you also know that the fast Fourier transform, FFT, is an algorithm that computes the discrete Fourier transform or the inverse. So it manages to reduce the complexity of computing the DFT from O of n squared, to which arises if one simply applies the definition to O of n log n, where n is the data size. This is because the DFT requires n squared multiplications and n squared minus 1 additions to compute the discrete frequency spectrum, while the FFT only requires n over 2 log n of each. The emphasis is usually placed on the difference in computational speed, which can be enormous, especially for data sets which n is large. However, this clearly involves an enormous energy efficiency improvement as well. So to examine this, one can perform a simple experiment using two Arduino Uno microcontroller boards, as shown here. I was actually planning on performing this experiment and performing several trial runs, but unfortunately I ran out of time getting the experiment up and running. However, this experiment can easily and safely be performed at home if desired. So one board can be used to perform the DFT directly from its definition and also the FFT. And the second board can be used to measure the energy consumed by the first board during implementation of these two algorithms. So the first board can simply contain a sound file in memory, such as the cleanspeech.wave file that we are familiar with from Project 2. To simplify the experimentation and ensure that both methods, the DFT and the FFT, have a baseline by using the exact same data for their implementation. You will have to shorten the file, however, if you do not plan to extend the memory capability of the Arduino and additional hardware, because yes, that 4-second audio file is too large to be stored in memory. So this is a realistic and practical experiment because the Arduino Uno utilizes a readily available microcontroller on board, the Atmega 328P from Microchip, which is inexpensive and can relatively easily be integrated into a custom application by mounting it on a breadboard or a custom designed printed circuit board. So here's a simple schematic of the proposed experiment setup. As you can see, the top Arduino is supplying 5-volt power to the bottom Arduino through a small resistor, such as 0.25 ohms. The small resistance value must be chosen to ensure that the bottom Arduino receives adequate terminal voltage even when running at full load. So the voltage drop across the resistor can be measured using analog inputs. And since the value of the resistor is known, Arduino can calculate the power consumed at each sample and use the basic formula power equals voltage times current, and use its internal clock to measure the time elapsed to determine the energy consumed. The bottom Arduino is obviously the device that will perform both the DFT and the FFT on the stored signal. And furthermore, the purple wire shown here should be used by the Arduinos to communicate when a trial run is started and ended, and to ensure the data obtained is actually representative of the algorithms being run. So finally, the results of each trial can simply be sent over the USB to the serial window on a connected computer. As I said before, I unfortunately do not have results to share at this time, but it should be clear here that smart algorithms can undoubtedly be used to significantly conserve energy consumption. The ability to select efficient algorithms for embedded or edge applications is a critical skill to have when designing devices for these applications. And in this case here, this might not even be the optimal energy consumption rate. So what I mean by this is that a lower bound on the complexity of the DFT implementation has actually not been rigorously proven. That is, it has not been proven that the DFT requires a minimum of n log n operations for correct implementation of the transformation. Evidently, no algorithms of lower complexity are known at this time either. So maybe one of you guys can come up with a solution to this problem, come up with a proof, and make a lot of money. So with that being said, I'm going to conclude my TED Talk. Does anyone have any questions?